welcome Mr. David MITZI from the Duke University in the US. Good morning.
Good morning.
Yeah, you're welcome.
Yeah, thanks.
The EMRS is a place where scientists of materials come together from all over the world. Can you say something about your personal highlights, or why did you decide to come here?
First of all, I really enjoy interdisciplinary science. My undergraduate degree was in electrical engineering. Okay. Then I did my PhD in physics or applied physics, and then I joined a chemistry group at IBM after graduating. And so I really love material science because it is interdisciplinary. It involves all those disciplines. And I came to the EMRS to learn, to understand what's going on in Europe, basically, in material science. I mean, my other conference that I really enjoy is the American analog, the American MRS, US MRS meeting. Yes. Which similarly gives a more United States slant towards what's going on in material science.
It has been in Boston, wasn't it?
Boston and also in Phoenix. So
okay.
The latest one was in Phoenix. I was there in April.
So you travel a lot.
Yes.
Okay. You are also one of the symposium speakers.
Yes.
Can you tell us something about it, your talk, what it will be like?
Yeah, the thrust, so first of all, my talk is in Symposium G, which is halide perovskites, lower dimensions for devices. And my talk focuses on the tunability of these systems. These are highly tunable systems. They have both organic and inorganic components to them. Okay. And I will give 3 examples of how we use the organic component to tailor properties of these structures for science and application. In one case, we use the organic cation to template the formation of inorganic layers that would not form otherwise. And these inorganic layers then have electronic properties that are desirable for device application. The second example, we use the organic cation to tailor the thermal properties, and in particular, we use the organic cation to enable, to allow these materials to melt. And so we can then melt process films and crystals. We don't need to use solvents, which are a waste product during the processing of these materials. So it's a greener process. And then thirdly, we've got an example of using organic cations that are designed to have electronic properties that are active in terms of how they impact the optical properties and the electronic properties of the material. So we can tailor the organic component to change the properties of the materials in ways that we design using computational chemistry.
Okay, interesting, very interesting. And if you have a vision for the future, what would it be? Regarding to your scientific field, of course.
Yes, I think all of the systems that I've looked at in my career can be considered complex electronic materials. So I started out looking at high-temperature superconductors, which consist of bismuth, strontium, calcium, copper, and oxygen, so 4 or 5 elements. I've worked also with these halide perovskites, which consist of organic and inorganic components of various dimensionalities. And I work on chalcogenide systems. So chalcogenides are materials that have sulfur, selenium, or tellurium in them. But we work in particular on multinary systems that have many elements and therefore are quite complex. And so throughout all of these systems, our goal is to look at these complex systems in order to instill tunability, but at the same time, this complexity can lead to defects that can either harm or help the properties. So we have to learn how to control the properties and defects in these complex systems to suit a certain need. And often the need we're targeting is in energy applications like solar energy.
Okay, this sounds really important and important work. And if you want to see and hear about more these topics, the symposium talk is tomorrow.
Tomorrow, yes,
It's not
Friday.
already done.
No.
Thank you for your time.
Thank you.